Today's the day we get to dive deeper into inverse functions. So to kind of think about this more generally, let's think of a biologist studying the number of bacteria over a given period of time. So every single hour, they're going to record the number of bacteria. So that's some function of time. We'll call it n. So after 1 hour, there's 100 bacteria, 200, 400, 800. So basically every hour, the number of bacteria is doubling. But now maybe instead we're concerned with the time it takes to reach a population level. So instead we're going to reverse those roles. So maybe for a culture, they need a certain number of bacteria. They want to know the time it takes for it to get there so they can perform this experiment. So in this case, instead of my input being time, I'm going to input the number of bacteria and I'm going to get my time in return. So my input is now n. My output is a function of n. So this is inverting those roles of the input and output. So these two functions are inverses of each other. The problem is not all functions are guaranteed to have an inverse. So let's look at a few examples. And the first one we're going to look at, it's some set D with inputs 1, 2, and 3. The outputs are going to be 4 and 5. So our function f, if you input 1, the output will be 4. If you input 3, the output is 5. And if you input 2, the output is also going to be 4. So this is going to be what we call our function f. Okay, so this is definitely a function because the input has one output. I only have a single arrow leaving each and everything in my domain. The problem is we can't reverse these roles of the input and output set because ultimately the result is not a function. So if instead I go ahead and switch what becomes my input and what becomes my output, I'm going to end up having 2 arrows leaving this input of 4. And that results in something that is not a function. So this particular input has multiple outputs, and that's a problem for us. So what we need to happen is we basically need to guarantee our y's don't repeat. So remember, to classify a function, your x's couldn't repeat. To classify something that has an inverse, not only do the x's not have to repeat, but your y values can't as well. So we need to basically guarantee we have unique y values for every input. So ultimately, we need to make sure that if x1 and x2 are different, so different x values, then the y values are also different to guarantee we have those unique outputs. So you may remember this property. These are called one-to-one functions. You have a couple of different ways to guarantee something is one-to-one. Remember, to find a function or see if something is a function, you had that vertical line test. You had to make sure your vertical lines don't intersect. For inverses, we want to make sure that a function passes that horizontal line test. So we have 2 ways to guarantee a function has an inverse. The first is a function has an inverse if and only if it's one-to-one. So here you show the graph passes that horizontal line test because this way every horizontal line intersects at one y value. The other way you can guarantee that happens is you show f is strictly monotonic on its entire domain. Then it'll be one-to-one and you're guaranteed it'll have an inverse. This word monotone means one for mono and tone, direction basically. So this function is always increasing on its entire domain or it's always decreasing. It's never going to change direction. And because of that, it will pass that horizontal line test. So to give you some kind of visualizations, if you want something that's monotone increasing, it's always going up, 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 up. So basically, the derivative is positive on the entire domain because it's always increasing. For something being monotone decreasing, it is always going down, 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 down. And so in this case, your derivative is negative on the entire domain. So if you don't necessarily know what the graph looks like off the top of your head, you can go ahead and take a look at the derivative. If it's always positive or always negative, then you're guaranteed it will have an inverse because both of these kinds of functions will always pass the horizontal line test. They will never hit your graph in more than one spot. All right, so let's try some examples. Let's determine if the function has an inverse. And so we're going to start with x cubed plus x minus 1. If you tried to graph this without a calculator, it's going to be a little bit difficult. You could go through the process we learned in chapter 4, but we just need to know if it has an inverse, so I don't need to go through all of those details. So instead, let's determine if the function's monotonic on its entire domain, which in this case is any real number. So if we take a look at the derivative, it'll be 3x squared plus 1. 3x squared is positive. If you add 1, it's positive. This thing is always positive for all values of x. So ultimately, f is monotone increasing. We are guaranteed that it has an inverse function. If I look at this next example, which is also a third degree polynomial, only difference is these signs have been switched. We can do the same thing, but in this case, if I go ahead and take a look at this derivative, it's 3x squared minus 1. 3x squared is always positive, but because I'm subtracting 1, I can't guarantee this is always positive or always negative on negative infinity to infinity, which is the domain. Because if I go ahead and plug in 0 into the derivative, you get negative 1. If I plug in positive 1, you get 2. So ultimately, this does switch from increasing to decreasing, so this function does not have an inverse. So essentially, the whole point of an inverse function is to swap these roles of x and y. A function being monotonic will guarantee that's going to happen. It passing the horizontal line test is going to guarantee that you can do that as well. So ultimately, we have a process for the way an inverse function is going to act. The notation that we're going to use is f with like a negative 1 power. You don't want to confuse it with an exponent, so thinking this means like 1 over f. That negative 1 power is purely acting as a notation for the inverse. So ultimately, it's going to act as follows. We have x, that's our typical input, y, that's our typical output. And so our function f is going to start at x, and we get y's in return. So ultimately, this is going to be the domain of f. It's our input. The output is that range. When we talk about the inverse function, we swap these roles. So y becomes the input, x becomes the output. So the inverse takes us back to where we started. So what set was the range of our function becomes the domain for our inverse. And vice versa, what was the domain of the function is the range of the inverse. So ultimately, this inverse function undoes the original. Because if I input x, I get this y. If I put that y back into the inverse, I land right back to where I started here, okay? So as a formal definition, we're gonna let f be a one-to-one function with domain A and range B. Then its inverse function, denoted f inverse, has domain B and range A, and is defined by the following. Your y is equal to the inverse of x if and only if these undo each other. So if I go ahead and evaluate both sides with f, you end up saying f of y is equal to x. So those roles of x and y swap. So as a result of this definition, we get two things. If I take the inverse and evaluate it at the function, those are going to just cancel each other out, and you land right back to where you started. And this is going to be true for every x that's in the domain of f. And likewise, if I go ahead and take f and evaluate it the inverse, these will cancel each other out, and you end up back with your input. This holds true for every x in the domain of the inverse, okay? Now, the other interesting thing, because these roles of x and y swap, if you have a point A, B on the graph of f, you switch x and y, so the point BA has to be on the graph of the inverse. So let's try to detect how this ultimately alters the graph of our function, or how we can utilize the graph of the function to get the inverse. So we're going to go ahead and graph the point AB, which maybe is up here. This line y equals x is going to be important because points like 2, 2 are on here. Well, when you switch x and y, you still get the point 2, 2. So anything that is immediately on this line is going to stay put. But if I go ahead and swap this now, I get the point BA, so my x and y are going to switch. So we're going to kind of just visually figure out what's going on. If I go ahead and connect these two, that distance is something. This is going to bisect it right in half. So these two are going to have exactly the same distance. The other unique thing is the distance here is basically the x distance out to this point. So this is a distance of A. And if I go ahead and look at this line segment as well, that is a vertical distance. So this is also going to be A. So ultimately, these two pieces are equivalent to each other. And if I look at the distance from the origin to the point AB, it gives me some distance. But if I'm just switching the order, it's not going to change that distance length. So these two are going to be equivalent as well. And then finally, this distance here is the y distance for this coordinate. So this is going to be length B. Here, this is a horizontal distance out to point BA. So this length is also going to be B. So this side is equivalent to this one. And then from our middle perspective as well, if I look at this straight line, I have a ton of similar triangles going over each other. So ultimately, these are reflections about this line, y equals x. So the point BA is found by taking the point AB and reflecting it across this line. Well, if you're going to do that for every single point, you're going to take the graph of the function and you're just going to reflect it across y equals x. So the graph of an inverse function can be found just by reflecting across y equals x. So let's take a look with the two functions we've heavily been working with. We've got that logarithmic and exponential function. If you think of y equals e to the x, it goes to the point 0, 1. You go ahead and switch those roles of x and y. That becomes the point 1, 0. So ultimately, this point gets reflected over here. The y-intercept turns to the x-intercept on the natural log. And this graph is indeed a reflection of those natural log. Okay? So if I don't know that a function is an inverse of another, or I'm just given an arbitrary function, how can we ultimately find that inverse? So typically you have f of x is equal to this expression. Really, you're just going to say that y is equal to this expression then. And because those roles of x and y swap, you're going to do exactly that. Anywhere you see an x, it's going to turn into a y. Anywhere you see a y, you change it to an x. Then you're going to solve that resulting expression for y, and that is going to be your inverse function. So you're not going to be able to do this for every single type because, again, if I go back up to some of these examples, looking at our first one, this has an inverse, but if I tried to do exactly that process, I definitely cannot solve y cubed plus y minus 1 equals x for y. That would be near impossible with the skills I have. So in that case, I know the inverse exists, but just finding it is going to be tedious. So let's try some examples where we can actually do that. Given that the function is 1 to 1, f of x equals the square root of 2x minus 1, we're going to find the inverse, and we want to find the domain and range of this inverse. So we can also kind of use our knowledge and connect to the earlier stuff. This is a monotonic function because if you do take its derivative, it's 1 over the square root of 2x minus 3. Square root's always a non-negative number, so this thing is non-negative, and that's going to be true on the domain of this function. So it definitely has an inverse. Now we want to actually find it. So instead of using this function notation, I'm going to replace that by a y. And I'm going to say y equals the square root of 2x minus 3. Now we want to go ahead and swap those roles of x and y. So this y gets replaced by an x, this x gets replaced by a y. If there were more x's over here, I would need to replace those by y's as well. So any x gets replaced by y. Now we need to solve this equation for y. So let's go ahead. We need to get that radical gone by squaring both sides. So this gives us x squared is 2y minus 3. Add that 3 over. Then we just have to divide by 2. And ultimately, this gives us our inverse function. So the expression we have here is the inverse. So 1/2 x squared plus 3/2 is going to be the inverse of a square root function. Now, if you think of the graph of a parabola, it's not 1-to-1, but if you do restrict its domain, you can go ahead and do that to find its inverse. So I'm only going to really use half of the parabola to get the inverse function. So let's think of our function f of x equals the square root. If I go ahead and consider this 2 underneath, all that's going to do is stretch or shrink my graph. And then if I work with this minus 3, because it's attached to the x, that's going to be a horizontal shift. So what's going to happen is our domain's going to be affected, but our range not so much. So the 2 just stretches or shrinks it. The minus 3 does the opposite, so it moves it to the right. So ultimately my graph kind of roughly looks like this, okay? So what we can do is we can find the domain and range of this pretty straightforward. For square root functions, you need what's underneath to be greater than or equal to 0. If I solve for x by adding the 3 over and then dividing by 2, immediately I get my domain as 3/2 to infinity. And the range, because I didn't have any vertical shifts added on the outside, is going to be from 0 to infinity. So when we go ahead and work with this expression to find my domain, I can just utilize the range of my original function. So my domain is going to have to be from 0 to infinity. Looking at this expression off the bat, though, I wouldn't know that because normally a parabola, you can do all real numbers. So this is where that restriction comes into play to make it 1-to-1. Now, when it comes to the range of this function, again, I'm going to do the same thing. The domain of my original function is the range of the inverse. So the range is going to be from 3/2 to infinity. So if I also think about trying to plot this one, this plus 3/2 is just going to shift this vertically. So ultimately, I have a parabola that's just been shifted upwards. To make it 1-to-1, we're going to ignore everything on the left half. So now the piece on the right half passes that vertical line test. Now we've got a little bit of a hand. We're going to look at a theorem that talks about some of the connection between properties of functions and their inverses. So let's let f be a function whose domain is some interval I. If f has an inverse, then the following statements are true. If your function's continuous on I and it has an inverse, we can go ahead and swap all those roles. The inverse is also going to be continuous on whatever its domain is going to be. If a function is increasing, likewise decreasing on its domain, when you flip that graph over y equals x, it's not going to change that property. The inverse function is also going to be increasing or respectively decreasing on its domain. So it keeps that property. If your graph was increasing, your inverse is going to have exactly the same quality. Now, if f is differentiable on an interval containing c, and as long as the derivative is not equal to 0, then the inverse is going to be differentiable at whatever that value was. So this is going to help us with finding the actual derivative of an inverse. And again, we don't necessarily want to find the inverse function because that can be tedious to go through. And ultimately, if we think of this kind of graphically, if I look at this point C and then the y value corresponding to it, the inverse is going to go through that y value, comma, the C. So ultimately, those roles of x and y swap. So this becomes the input into my inverse function. And this line is going to give us the derivative of f at this point c. So if I flip this whole graph over, what that's going to do is still give me the slope of the tangent line, but now it's going to be at the point f of c instead. So there is going to be a connection between the derivative of a function and the derivative in an inverse. And purely because they are going to flip-flop and swap those roles, basically the inverse is going to be the reciprocal of each other. But to actually come up with a closed form expression for it, we're going to go back and we're going to use our implicit differentiation. So we want to look at the derivative of an inverse function. So let's let f be a function that's differentiable on some interval I. If f has an inverse function, f inverse, then this is differentiable at any x as long as this interesting expression does not equal to 0. And ultimately, its derivative is going to be given by the following. So if I want to take the derivative of an inverse function, it's going to deal with the function itself, and it's going to deal with this unique expression here. So the derivative is going to be given by 1 divided by the derivative of my original function evaluated at my inverse, as long as this denominator is not equal to 0. So where the heck does this thing come from? It's quite an interesting looking expression, and it doesn't make you actually find the inverse function in any way, shape, or form, because you're going to evaluate it in an inverse function, but oftentimes we're just evaluating at a specific point. So really, if I know stuff about my original, I'll know what point I need to plug in here. So let's take a look as to why this is true. Remember, we're going to let y represent the inverse function. Because of the roles, if I go ahead and evaluate both of these at f, these two are going to cancel each other out, and this is equivalent to saying f of y is equal to x. Now, using implicit differentiation, I can go ahead and take the derivative of both sides with respect to x. So we want to take the derivative of x on the left-hand side, derivative with respect to x on the right-hand side. Right-hand side's definitely easier. This variable matches what I'm taking the derivative with respect to, so the derivative of the right is 1. If I go ahead and take the derivative of f of y, kind of thinking again of my chain rule, I get the derivative of the outer, don't touch the inner at all. But because this variable is something other than what I'm taking the derivative with respect to, you get that y prime attached. So we're going to go ahead and we want to solve for y prime, which means we've got to divide by this quantity. So we're going to take both sides and divide by f prime of y. Now, going right back up here to the very beginning, if I need this y expression in here, it's really the inverse function. So immediately that tells me y prime is 1 divided by the derivative of our original function evaluated at the inverse. Okay? So that's where this expression comes from. We're going to take a look at the type of examples that you're going to see in your homework. But ultimately, we can find the derivative of an inverse without finding the inverse function itself. Okay? So let's try some examples. Let's let f of x equal 1/4 x cubed plus x minus 1. First thing we want to do is figure out what is the value of the inverse function when x equals 3. So this is basically trying to figure out if I plug in 3 into the inverse, what is that going to give me? But I don't have an expression for the inverse at all. I only know about the actual function. So instead of finding the inverse, what I can do is figure out where does my function equal 3? Because remember, those roles of x and y switch. So this is the input into my inverse. It's the same thing as figuring out where is the output give me 3 for my function. So I want to solve this equivalent expression. And that's a little bit easier. So I want to figure out, where does 3 equal 1/4 x cubed plus x minus 1? Moving over 3 to the other side just gives you a -4. And this still isn't the easiest to solve, but this is something I can definitely plug into a graphing calculator. So if I look at this graphing calculator, I want to see, where does this equal 0? And looking on that expression, it exactly happens when x is equal to 2. So this is telling us x equals 2. So ultimately, what that means is our function goes through the point 2, 3. The inverse has to go through the flip of that. So f inverse goes through the point 3, 2. So ultimately, if I plug 3 into my inverse, my output will be 2. So that is the value of the inverse function when x is 3. Utilizing that, we now want to see, what is the value of the derivative of the inverse when I plug in 3. Using our expression, I'm trying to calculate this derivative. That's equal to 1 divided by the derivative of my original function, evaluated at f inverse of 3. But f inverse of 3 is just 2. So really, all I'm going to do is find the derivative of my function, plug in 2. 1 over that will be the derivative of my inverse. So since our function is equal to this expression, the derivative, just applying some power rules, is going to be 3/4 x squared plus 1. If I plug 2 into that, it's 3/4 times 2 squared plus 1. 2 squared is 4. Times that by 3/4 gives you 3 plus 1. This is equal to 4. So this expression down here is going to be 4. So ultimately, if I take the derivative of my inverse and I plug in 3, I'm going to get 1/4. So the thing you want to notice here is that when I plug in 2, I get 4. And remember, our function goes through the point 2, 3. When I plug in 3 and into the inverse, my inverse goes through the point 3, 2. My slope of my tangent line is going to be 1/4 instead. So you want to notice that these two are reciprocals of each other. Because those points flip, the derivatives are going to literally flip. So you get reciprocals each time. So let's try another example. We've got a function f of x equals x cubed minus 1. This one's not too bad. You could actually find the inverse function. But I'm still going to go through the same process. I want to figure out, what is the value of the inverse function when I plug in 7. And so this being the input of my inverse is the same thing for solving, when does my function have an output of 7. So instead, I'm going to figure out, where does my function equal 7. That's equivalent to saying x cubed minus 1 is equal to 7. Go ahead, add 1 to the other side. If you want x cubed to equal 8, the only way that can happen is going to be when I plug in 2. So my function f goes through the point 2, 7. My inverse is going to go through the point 7, 2. So ultimately, f inverse of 7 has an output of 2. And now I can utilize that to figure out, what is the derivative of the inverse function when my input is 7. So again, following that same process, we're going to take 1, divide it by the derivative of our original function, and I'm going to go ahead and plug in the output of my inverse function at 7. So really, I'm going to take the reciprocal of what happens when 2 is my input into my derivative. Okay? So I know my actual function. It's x cubed minus 3. The derivative is just 3x squared. I want to plug 2 into this, so that's going to be 3 times 4, which just gives us 12. So when x is equal to 2, I'm going to have a slope of 12. Now I want to see, when x is equal to 7 for my inverse, what is the slope of that tangent line? And all it is the reciprocal. So the derivative of my inverse function evaluated at 7 is going to give us 1 over 12. And again, these are reciprocals of each other. Because ultimately, when you're flipping that tangent line over y equals x, it's going to change. If the rise over run was 12, the rise over run is now going to be 1 over 12. So those flip. So let's try one last example. This one's a little bit of a trick one. Given f of x equals cosine of 6x, for x between these values, we want to find the derivative of the inverse evaluated at 1. And so what I need to do is I need to go ahead and take 1 divided by the derivative of my original function evaluated at f inverse of 1. Okay. So I need to figure out what is f inverse of 1. And that's going to get plugged into the derivative of cosine of 6x. So I need to figure out really where does f of x equal 1. So where does cosine of 6x equal 1? Specifically on this interval, because there's a lot of places where cosine of 6x would equal 1. So on that interval, cosine of 0 is 1, cosine of pi is 1, cosine of 2 pi is 1. All of those give us those options. The only place that can really happen for then is if this inside is equal to 0. So if the inside is equal to 0, then cosine of 0 will give me 1. So really, if I plug in x equals 0, that's going to give me cosine of 0, which is 1. Okay. So ultimately, if my input is 0 for my original function, my output is 1. So when we evaluate the inverse at 1, it's going to give us 0 as an output. So x and y are going to swap. So ultimately, if I want to then take the derivative of my inverse evaluated at 1, it's going to give me 1 divided by the derivative of my original function when I plug in 0. Because these roles, again, swap. Right? So now we need to see, okay, we've got the original function. What is f inverse of 0? So if we have f of x equals cosine of 6x, the derivative will be negative 6 sine of 6x. And I run into a bit of a problem. If I plug in 0, I get sine of 0, which is 0. So if I try to take the reciprocal of this, I get 1 over 0. Ultimately, that means it's undefined. So I would get 1 divided by this. Unfortunately, my inverse function does not have a tangent line when x equals 1. Let's try one more. Same thing again, I want to go ahead and find the derivative of the inverse evaluated at 0 for this particular function. And now we run into some fun problems because the input is going to be a bound in our integral. So using our same process, if I want to take the derivative of the inverse, it's going to be 1 over the derivative of the original function evaluated at the inverse evaluated at 0. So ultimately, I need to find two things to go ahead and find this quantity we want. I need to find f prime, so I need to differentiate this original function. And I also need to see what is f inverse of 0. So we need to find these two quantities. I'm going to start by finding f inverse of 0. That's the same thing as figuring out where does f of x equal 0. So ultimately, when does this expression from 4 to x of this inside equal 0? And that seems a little messy because what do I plug in up here? I definitely don't want to find the antiderivative of this thing. I have no idea how to find the antiderivative of that. So I need to think about this in a bit of a different way. Since this is finding the area of the function from 4 to some point, if you think of finding the area from 4 to 4, It's nothing. The area under a single point is nothing at all. So ultimately, I want to make that connection. If I try to integrate from 4 to 4 of any function, it's going to give me 0. So ultimately, the number I can plug in for x is 4 to give an output of 0 for this function. So then if I go ahead and put 0 into the inverse, the output is going to be 4. So I have one of the quantities that I want. So I'm going to go ahead and evaluate my derivative at 4 in this expression. So now we need to find the derivative of our function. Again, that variable x is going to be in the limits of integration. So if I'm going and taking a derivative, I'm just applying that fundamental theorem of calculus. We go ahead and evaluate that expression at x. So I get 1 over the square root of 5 plus x to the 4th, times it by the derivative of x, which is just 1. So if I want to plug in 4 for this, I get 1 over 5 plus 4 to the 4, which ends up being 261 under that radical. So if I want to find the derivative of my inverse evaluated at 0, I get 1 over this expression. F inverse of 0 is 4. So I really get 1 over the derivative I just calculated. So it ends up being the reciprocal of this quantity, because we get 1 divided by a fraction. And when you divide by that fraction, it's like multiplying by the reciprocal. So really, the second I have the derivative of my function, I go ahead and just flip it, and that's going to give me the derivative of the inverse at that equivalent point. So you can see there are different inputs here, but that's because those roles of x and y swap. So in the next 2 sections, we're going to go back and revisit the exponential function. We'll go through the derivative and likewise the integral of our e to the x or e to a function of x expressions. And then we're going to take a look at bases other than e. So far the only thing we've done is work with e to the x, and we've taken derivative of the natural log function. So we want to go ahead and see those connections.